Okay, continuing 9.5, alternating series. Problem number C, or letter C. We have an alternating series, and we know that our a sub n, if we just looked at that sequence, we put a 1 in, we're going to have 1/2. We put a 2 in, 2/4, 3 in, 3/8, 4 in, 4/16, dot, dot, dot. And we need to start, and of course, these two are equal, the first two, but I think that since it says a sub n plus 1 is less than or equal to a sub n, we're going to be okay. I notice that they're all increasing. Well, I mean, they're all positive, excuse me. And I notice that each one is smaller than or equal to the next. Or why do I keep saying that in a funny way? It's decreasing in magnitude, okay? This is number 2 is the one where you are saying, is it decreasing in magnitude? And it can be equal to, but has to be decreasing in magnitude as n goes to infinity. And it is. Number 3, the limit as n goes to infinity of your a sub n, so this would be of your n divided by 2 to the n. We have to figure out what this is. And remember when I talked about the exponential functions like 2 to the n or 3 to the n or 10 to the n and how strong they were and how fast they got huge. When you look at this one, the n in the numerator means nothing to 2 to the n as it goes to infinity. So this does go to 0. If you would like to look at it, if you would like to graph that sequence n over 2 to the n and look at it in your calculator, you could see that sequence, as n goes to infinity, your values are going to 0, okay? So you could look at that on your calculator, but that is true. So therefore, we have convergence, okay? So this one converges. All right, letter D. This one is a strange one. We have to really do some work to get this one to be understood. So if I start putting in my values, when my n is 1, I get 0. When my n is 2, I get the natural log of 2 over 2. When my n is 3, I get the natural log of 3 over 3. When my n is 4, I get the natural log of 4 over 4. So I'm really curious if this is decreasing in magnitude, and I'm also curious, is ln of 4 over 4, what is that approaching, ln of 3 over 3? So we want to go ahead and use the derivative to prove decreasing. Because as n goes to infinity, it has to be decreasing. It doesn't have to be decreasing the whole time, but as n goes to infinity, it has to be. So if I look at f of n as my ln n over n, and I look at taking the derivative of it, I have to use the quotient rule, low d high, minus high d low, over the square of what's below. I end up with 1 minus ln n over n squared. And I want to set that equal to 0. So that means I'm looking to see where that is 0. So if I move my negative over, I'm looking to see where the natural log of n is 1. Remember, this means e to the 1 is n. So n equals e here. So that is my critical point. And I would want to look at, since e is 2.71, put a 2 in, and you can use your calculator, and you should get that this is positive. If you put a 3 in, you should see it's negative. So we have increasing function, decreasing function. So it is in a little funny situation because it's not decreasing the whole time. but it is decreasing as n goes to infinity. So I'm just gonna write here, just so you guys can remember, and you might want to write this too. Note, this sequence ln divided by n initially increases from n equals 1 to n equals e. Although we're not really using e, right? So really it's only for 1 and 2. And then at 3 we're fine. But, and then decreases to infinity. So we will see that as decreasing as n goes to infinity. Okay? So you have to kind of tell yourself this before you start solving this. So number 1, a sub n is greater than 0. And for that one, you might want to say, well, it's not negative. Because 0 is neither negative nor positive, right? Number 2, a sub n plus 1 is less than or equal to a sub n as n goes to infinity. So that needs to be, you know, stated as n goes to infinity, because it's actually not always less than or equal to. And then number 3, the limit as n goes to infinity of ln n over n. And if you put this in your calculator, you'll see that it is approaching 0. Put it as a sequence, you can see that it's approaching 0. So that limit does go to 0. So therefore, this alternating sequence actually converges. Okay, so that one does converge, even though it was a weird one. Okay, that was a really weird one. So now, alternating series error bound. This is going to have a lot of vocabulary in it that you might not be comfortable with yet, but just bear with me. For some convergent alternating series, the partial sum, S sub n, is a useful method to approximate the sum S of the series. We call the error that is involved in using S sub n as an approximation for S, the remainder, where R sub n is equal to S minus S sub n. If a convergent alternating series satisfies the condition a sub n plus 1 is less than or equal to a sub n, then the absolute value of the remainder involved in approximating the sum S by S sub n, which would be your absolute value of R sub n, is less than or equal to the first unused term. That is, the absolute value of S minus S sub n is equal to the absolute value of R sub n, which is going to be less than or equal to a sub n plus 1. In other words, if the three conditions, alternating, decreasing in magnitude as n goes to infinity, and having a limit of 0 are met, you can approximate the sum of the series by using the nth partial sum, S sub n, and your error will be bounded by the absolute value of the first truncated term. So what's a truncated term? Like, so for this next one, this function, or this series, we are taking and we are finding the S, oh gosh, what did I hit? Sorry. We are finding S sub 9 here. Because look, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. That is my 9th partial sum of that series. And what they're saying is we basically truncate it. So that means we just like stop and chop it off. But we can find the error by looking at the 10th term. So the absolute value of my error is going to be the absolute value of the 10th term, right? A sub 10 or whatever, the 10th term. I didn't want to put R sub 10, but that's fine. Absolute value, sorry, of the 10th term of the series, okay? Because we did S sub 9, it's the next term. So if we were looking here, you can see that it's like 2 squared, 3 squared, 4 squared, 5 squared in the denominator. So 9 squared, this is going to be a negative, and it's going to be 10 squared. So this is actually going to be negative 1/100th. Therefore, the error in my approximation is the absolute value of that. So my error is going to be 0.01. So that's basically how close we are to getting the actual answer. It's the exact same, right? For a certain number of places. Less than 0.01. So use your calculator to find the sum of the first 200 terms. So what I did was I went to Desmos, and if you go to functions and go to miscellaneous, when you first go to functions, you're at trig, and then you go to miscellaneous, then you have summation, and oops. So I guess I can do this again. Functions, summation, n equals 1. To 200. And then this would be negative 1. And then put that up there. This is the only way I know how to do this. And then backspace. I back arrowed and then backspace. Now you have to put this in parentheses. And this is your n plus 1. If you don't put it in parentheses, it won't let you put everything up there. And then I need to do times, and then we'll do 1 divided by n squared. And notice that it's, before I even hit return, it already gave me that answer. So 0.8224545959923. So I'm going to go back to my notes, because I got my calculator value here now, 0.8224545959923. And then what is the error in your estimation from the first, or from the 200 terms? Well, it's going to be the 201st term. And so the way this is set up, if you put an odd value in, you get a positive. If you put an even, you get a negative. So since I'm doing 201st, well, it doesn't matter because I'm going to take the absolute value of it. So the absolute value of negative 1 over 201 to the second. Is that going to be, that? Oh no, that's going to be my odd. So yeah, it's going to be odd, so it's going to be positive. Okay. Oh, so I made it negative. Never mind. Anyway, absolute value of 1 over 201 to the second power, because I'm 1 over n to the second. So I'm looking at my 201st term, because remember it said the first unused term, you know, so when you're truncating it, the first one that you would be chopping off and the rest of them, you know, so this is less than 0 point, and then there's 4 zeros after that to the right of that decimal point, 25. So that's a pretty good estimate. And I mean, I think, do you see how you had the first two terms were exactly the same? You know, so now you're saying that the first 4 terms are exactly the same as the actual answer if we put infinity in. Okay, so now example number 3. Approximate the sum S of the series by using its first 4 terms. So this is going to be your S sub 4. And when I put a 1 in, I'm going to get 1. When I put a 2 in, I'm going to get negative 1 over 2. Now remember, 1 factorial is 1. 2 factorial is 2 times 1, so that's 2. 3 factorial is 3 times 2 times 1, that's 6. 4 factorial is 4 times 3 times 2 times 1. So that's going to be 24. Okay, so we're going to be using all of those. So now, when n is 3, we're going to have positive 1 over 6. And then when n is 4, we're going to have negative 1 over 24. So if we added all those up in our calculator, we would get 0.625. So that is your approximate, you know, your partial sum of the series. And we could calculate how close we are by looking at the 5th term and taking the absolute value of that and looking to see that it would be less than, you know, whatever that 5th term is going to be. So it says, explain why the estimate found in A differs from the actual value by less than 1/100th. So we're going to say that the terms of the series alternate. Decreasing in magnitude comma, and have limit of 0. Therefore, the absolute value of the remainder is the absolute value of the error, which is the absolute value of R sub 4, which is going to be the absolute value of S minus S sub 4, which is less than the absolute value of the 5th term. And so our absolute value of error is less than 1 over 5 factorial. And if you did 1 over 5 factorial, so 5 factorial is going to be 5 times 4 times 3 times 2 times 1. So that's going to be 120. So that's 1 over 120. You can see that is going to be less than 1 over 100th. So now you've just proved that your error is less than 1/100th. And then it says, use your results to explain why S can't be 0.7. So you've got your S sub 4 minus your error, and you've got your S sub 4 plus your error. So your S has to lie between these two. And so this would be 0.61666 if I put that in my calculator on the left, and 0.6333 if I put that in my calculator on the right. So my actual sum will lie between these two values. And so that means that S can never be 0.7. So that's how you proved it. Okay, so now absolute and conditional convergence. A series can be classified as one of the following. A series, summation A sub n, is called absolutely convergent if the series of absolute values, summation, absolute value of A sub n, is convergent. So if they're both convergent, notice we're talking about the series that does not have an absolute value sign on it is convergent. The series with the absolute value sign on it is convergent. So if they're both convergent, then we call it absolutely convergent. If this series that doesn't have an absolute value sign is absolutely convergent, then it's convergent. Okay, so whatever. Absolutely convergent just means convergent. A series where the A sub n is convergent, so A sub n is convergent, but the absolute value of A sub n is not convergent, that one is called conditionally convergent. So it's only, if it's only convergent when summation A sub n is convergent, but if I took the absolute value of it, it would not be, then we call that conditional convergence. Okay? So now let's work a few of these problems. So we've got alternating series. My A sub n, actually you want to look at the absolute value on this one of your S sub n, because we are trying to figure out whether it's conditionally convergent or absolutely convergent, or if it's divergent. So we know that absolute and conditional convergence relies on the fact that you are comparing the absolute value to the actual, okay? So if I took the absolute value of S sub n, that is going to be my 1 over n. It's basically what we've been doing when we've been talking about our sequence. So if we looked at this as a sequence, and we kind of just listed our sequence values, that's what we were doing before. But now when we're trying to determine absolute convergence or conditional convergence, we're going to say, hey, if that, plus 1 minus 1 plus 1 minus 1 wasn't there, that's the absolute value of it. So all that would be left is that 1 over n. Well, we know that that is a divergent harmonic series. Divergent P series, right? It's the harmonic series. Your A sub n sequence, your 1, 1/2, 1/3, 1/4, ... that is the sequence, right? But your summation, so this is the absolute value of S sub n is really, I probably should have put summation 1 over n is the divergent P series. So please include that summation. I didn't include it in my notes, but now that I'm talking to you guys about it, I realize that I should have. So now we're going to look at, is this one that's not the absolute value, is the alternating one convergent? So now we're going to go back to, so we should say to ourselves, is the alternating series convergent? And I think you know this answer, but we're going to just do it anyway. So now we're going to go through our 1, 2, 3 test for alternating series convergence, right? Are all my A sub n's, which I listed right here, greater than 0? Yes. Are my A sub n plus 1's less than or equal to my A sub n's as n goes to infinity? Yes. Is the limit as n goes to infinity of my 1 over n equal to 0? Yes. So the alternating series converges, but the absolute value series diverges. Therefore, this one is going to be conditionally convergent. Okay, so letter A is conditionally convergent. All right, oops. Now let's look at letter B. Summation, n equals 1 to infinity. If I take and look at S sub n, it's going to be summation 1 over n squared. Right? Without the negative 1, positive 1, negative 1, positive 1. And I know that this is a convergent p-series with p equals 2, which is greater than 1. Okay, so that's how we know it's convergent. And now I want to find out, is the alternating one convergent? If they're both convergent, then we have absolute convergence. Okay? So now, number 1. Well, we should look at our a sub n. Okay? Our a sub n, our sequence is 1 over 1 squared, 1 over 2 squared. 1 over 3 squared, right? Well, they're all, decreasing, okay? And they're all greater than 0. So the first thing, they're decreasing. Second thing, or first thing, they're greater than 0, sorry. Second thing, they're decreasing as n goes to infinity. Third thing, the limit as n goes to infinity of 1 over n squared is 0. So therefore, the alternating series converges. Well, if the alternating series converges and the absolute value series converges, we then have absolutely converging. Or convergent, I guess. Absolute convergence. So it's absolutely convergent. So letter B, absolutely convergent. Letter C, okay, if I took off that negative 1, positive 1, negative 1, positive 1, and just looked at my absolute value of my summation, that would be summation 0.01 to the n. Hopefully that looks familiar. We could also say summation 1/100th to the n. I hope you're saying, oh, that's a geometric series. So it is a convergent geometric series with r equal to 1/100th, and so my r is between 0 and 1, so it's convergent, okay? So now we need to start looking at, is my alternating series convergent, right? That's the next question. So number 1, and it'd be 1 over 100 to the 1, 1 over 100 to the 2, 1 over 100 to the 3. Are all my a sub n's greater than 0? Yes. Are my values decreasing in magnitude? Yes. Oops, as n goes to infinity. Yes, they're decreasing in magnitude. And remember, that'd be because it'd be 1 to the n over 100 to the n, right? So then it'd be, so it'd be like 1 to the 2 over 100 to the 2, 1 to the 3 over 100 to the 3. So you can see they're decreasing. And then number 3, the limit as n goes to infinity of 0.01 to the n is, of course, 0, because that denominator, the numerator keeps staying 1, the denominator keeps getting larger, larger, larger. So therefore, my alternating series converges. Well, my alternating series converges and my absolute value series converges, so therefore this one is absolutely convergent. All right, now let's do D. So D, it doesn't seem to be alternating unless you think about it as when n is 1, that's the cosine of pi, that would be 1, or no, that's negative 1. Cosine of 2 pi is 1, cosine of 3 pi, negative 1, cosine of 4 pi, 1, cosine of 5 pi, negative 1. So this is what makes it alternate. So this is your alternating piece. Okay, and so when you take the absolute value, you only have the summation of 1 over n squared. So this is a convergent p-series with p equals 2, so p is greater than 1, so therefore it's convergent. Now we want to find out, is the alternating one convergent? So first, are all my a sub n's greater than 0? Yes. Okay, so if you were thinking about, 1 over 1 squared, 1 over 2 squared, they're all greater than 0. Number 2, are they decreasing in magnitude as n goes to infinity? So think about that. Yes, they are decreasing in magnitude. The limit as n goes to infinity of 1 over n squared is 0. So therefore, my alternating series